In this video, lesson number 4, part 3 of Unit 2 in Calculus, I'm just going to run through a bunch of practice problems for implicit differentiation. Now I do have an answer key for all of these that I'll go ahead and release and post on our Schoology page, but I've just got a selection. Every group of 4 problems or so, we'll go ahead and work through a sample for you to compare your process against. So in this first group of 4, I think I'd like to take a look at number 3. Now keep in mind with implicit differentiation, it's as if we're applying this derivative command, if you want to think of it as such, this d dx, to all components of the equation. And it gets to be a little bit messy to try to squeeze them in here, so it is worthwhile to rewrite this on another sheet of paper or off to the side. And that looks a little bit better. For this problem, I think I'll have enough room to work, but for others, I may not. So if you run into that issue, not having enough room to work, then by all means, complete these problems on a separate sheet of paper. Now, on the left-hand side, we're being asked to find the differential with respect to x of 2x cubed. Well, that's easy to do since the variables match. We'll go ahead and call this 6x squared. On the right-hand side, I'm using that mini chain rule. 2 times 3 is 6y to the first power. But since we don't know the differential of y with respect to x, then we turn around and multiply by dy dx immediately after computing this derivative in terms of y. The derivative of 5, a constant, is just 0, so we don't need to include that. And now to isolate dy dx, we could divide both sides by 6y. We have 6x squared divided by 6y, which of course would be simply x squared divided by y. And if I compare that to my answer solutions, well, that appears to be pretty much the same. I didn't show as many steps in the solution key, but we did end up at the same result. For the next set of 4, I think I'd like to take a look at number 7. You'll notice in this group that it looks like all of them have several terms that contain y variables raised to a different power. So that's what makes this group a little bit different than the last. In the interest of space and time, I'm not going to write or rewrite this expression with the differential notation surrounding it. Instead, I'm just going to compute the derivatives. So this is a derivative of y with respect to x. So I'm going to use the chain rule here. We'll call this negative 8y to the first power, and then we immediately multiply by dy dx. We don't know the derivative of y with respect to x. That's what we're looking for. In this term, we'll again use the chain rule. We'll call this 6y squared, but again multiply by dy dx because we don't have that differential. And then finally, on the right-hand side, the derivative of x squared is 2x. And we know what the derivative of x with respect to x is. I mean, the variables match. And so if we follow the pattern that we established before, maybe this will help you understand dx dx, well, that's technically just 1, isn't it? So we don't generally write that following our differential. We'll just call this 2x. Now dy dx does act as a common factor, so we've got dy dx factored out of the terms negative 8y and 6y squared. So ultimately, when we need dy dx, we're left with 2x divided by negative 8y plus 6y squared. That's pretty good, but I do notice that there's a common factor of 2 in all of these terms. So I'll call this x divided by negative 4y plus 3y squared. And I would probably call that a good final answer. And if we compare that to the answer key, looks like we got the same thing, x divided by negative 4y plus 3y squared. In the next group of 4, I've selected 10 to work through. This time we're going to end up using the product rule as part of our implicit differentiation. So here we go. The derivative of negative 5x in terms of x is negative 5. The derivative of 4 is 0. The derivative of x squared is 2x. And the derivative of this, I'm going to treat this as a function and then y by itself as a function. So when we use the product rule, I need the derivative of 2x squared, which is 4x, times the second function untouched, plus the first function untouched times the derivative of the second dy dx. I don't really need the grouping symbol here, but I chose to write it. Write it here because it reminds me that everything inside the grouping symbol is the derivative or the differential of this singular term. But I'm just going to take the grouping symbols off now so that I have a better look at what it's going to take to solve for dy dx. Well, it looks to me like I can subtract 2x. I could also subtract 4xy and then divide by 2x squared. And in those three steps, I'd be able to isolate dy dx. So since we're in calculus now, and I trust that your algebra is pretty strong, we don't need to show all these intermediate steps. We can do them all in one shot. So we've got this negative 5, take away 2x, take away 4xy, and that entire group is being divided by 2x squared. And I think that would be a good differential in terms of x for y. And if we compare that to the key, I think we've got a good match. Moving on to the next page, within this group of 4, let's take a look at number 14. This time we're going to be using the product rule twice, it looks like. And just as a preliminary thought, I probably will make this as a function and treat this as a function, and then 2x and y as the separate functions. So here we go. The derivative of the constant 4 is 0, and the derivative of 4x is 4. For this first product rule, the derivative of 5x cubed is 15x squared. So we take the derivative of the first function and multiply it by the second function untouched. To that we add the first function untouched times the derivative of the second. Now the derivative of this guy, of y squared, is going to be 2y, but since y is different than the x variable that we're differentiating against, we've got to turn around and multiply by dy dx immediately. And that grouping symbol shows the derivative of this term here. Similarly, this last term requires the product rule, so we'll take the derivative of 2x, which is 2, and multiply it by the second function, untouched. We'll add the first function, untouched, times the derivative of the second, dy dx. And again, since all of these terms are being added together, there is no need for the grouping symbols. So we'll just erase them, get them out of our way, so that we can see a better approach towards isolating dy dx. So I probably will do this in 2 steps, but it looks like I can subtract off the 4, the 25x squared y squared, and this 2y. That way those will move to the opposite side of the equation. And when that's done, since I've seen this trick before, I'm going to factor out the dy dx by dividing off the 5x cubed 2y and the 2x term. So let's see if we can do that in a couple steps here. So step 1, negative 4 minus 25x squared y squared minus 2y is equal to, and I'll go ahead and factor the dy dx out right now, because in a sense this, and this is now gone. So what we're left with is dy dx, a common factor, to the terms 5x cubed times 2y. Well, let's go ahead and combine that. We'll call that 10x cubed y and 2x. Now when we divide both sides, we're left with dy dx equals negative 4 minus 25x squared y squared minus 2y, that entire group, divided by 10x cubed y plus 2x. And I think we've got ourselves a derivative. I feel pretty good with that answer, and if we check it against my answer key on the other page, it looks pretty good, but I noticed there's a typo here. I got the y squared in this row, but I forgot to include it in the final answer. And I believe we've got a match for the dy dx that we just computed in this example. Except I've got a 25x squared here. How did I get a 25x squared? Did I make a mistake? Algebra gets you every time, doesn't it? Hopefully you caught my mistake and started yelling at the screen immediately. 3 times 5 is not 25, but instead it is 15. So we should have had a 15x squared, 15x squared, and then 15x squared. Okay, now this matches the answer key that I've got on the other page. We caught 2 small mistakes, 1 on each, and now I've gone back to the computer in which I generated this worksheet on and looked at its answer key, and it's got the same answer that we have here now. So I feel much better about number 14. But again, this example just goes to show that while the calculus, the process for the calculus component is pretty, what I would say, straightforward once you learn the techniques, it's the algebra, the simplification of algebra that can catch you, could cause you to make a mistake. Now for the last group of questions on this handout, the instructions ask you to use a graphing utility, and they recommend that you go to Desmos, and I still recommend that as well because graphing these implicit equations on Desmos is going to be a little bit easier than using our TI Inspires. If we've got time to investigate this, I'll show you how to do this next week when we see each other in class, but it's not critical, so we'll just use the quick and dirty approach for Desmos. So we'll plot the equation to see what the function or the equation looks like, and then we'll use implicit differentiation to find dy dx at a given point. So the equation is 2y cubed plus 1 equals 3x. So if I switch over to Desmos, we can write that equation. Try to bring up the on-screen calculator from the website. 2y to the third power plus 1 equals 3x. There we go. So there's the implicit function, or equation, I should say, and we would like to know the equation of the tangent line at the coordinate 1, 1. So you might be taking a guess right now, trying to figure out what the slope is there, but why guess when you've got calculus on your side? Let's go ahead and use implicit differentiation to find the slope. And I guess that's all that the instructions ask for, but I might find the equation of the line just for extra measure. So the differential for this particular example in terms of x would be 6y squared dy dx plus 0 equals 3. And when we isolate dy dx, we need 3 divided by 6y squared. This 3 and the 6 will reduce to 1/3. And if I evaluate dy dx at the coordinate 1, 1, then we have 1 over 3 times 1 squared, which equals 1/3. So that's technically a stopping point for this particular question. Except, Mr. Ehrman, you've got to get your algebra brain working a little bit better. If the numerator is divided by 3 and the denominator is divided by 3, we are left with 2 when factoring that 6. So come on, let's get it right. So we've got 2 times 1 squared, so we've got a slope of a half. That's a little bit better. Now to find the equation, y minus 1 equals a half times x minus 1, and we've got a half of x minus a half. When we add 1 to both sides, we've got 1/2 x plus 1/2. So this would be the equation of the line tangent at this particular point, and let's go ahead and check. If we graph the equation, y equals 1/2 x, let's get that x out of the denominator, 1/2 x plus 1/2. It sure looks like that line is tangent, that green line is tangent to the red curve at that specific point. So I'm pretty satisfied with that. It's a good thing I didn't have 1/3, because that clearly would not be a line tangent at all. Let's try one more example and then we'll wrap up this video. Okay, in number 23, the differential with respect to x. Well, this derivative, 3x cubed, is going to turn into 9x squared. The differential applied to negative 4y squared becomes negative 8y to the first power times dy dx. And the derivative of y is simply dy dx. So these two are common factors, so we'll say that 9x squared is equal to dy dx times negative 8y plus 1, and then dy dx by itself must be 9x squared divided by negative 8y plus 1. So we'll graph this and the tangent line in just a second, but what I would like to do is evaluate the derivative of y with respect to x at the coordinate negative 1, 1. So that means I need 9 times negative 1 squared, and I need negative 8 times positive 1 plus 1, which would be 9 over negative 8 plus 1, which equals 9 over negative 7, or negative 9 over positive 7. That would be fine as well. Now I know I'm running into 24 here. This would be a good case for me to work on a separate sheet of paper. But just to finish this out, let's see what happens if we find the equation of this tangent line. So setting up the point slope formula and then simplifying might look something like this. Negative 9/7 x. Now this becomes a positive 1, and negative 9/7 times positive 1 is still negative 9/7. On both sides I'm going to add 7/7. That way I've got a common denominator, and I'm still adding 1 to both sides. We would end up with y equals negative 9/7 x minus 2/7, and that would be a good equation of our tangent line. So this worksheet really did just ask us to stop here and calculate 9 over negative 7 as the slope at that particular point. But let's see how we did as far as the graph of the function at that point and the line that's tangent at that point. Let's see if we've got a good match. So here's a graph of the original function, and I'll zoom in a little bit so that you can see its unusual behavior. We have a coordinate on the graph located here at negative 1, 1. And as predicted, the equation negative 9/7 x minus 2/7 does represent a tangent line to the black graph at the red dot. So I hope this video helps. I really just wanted to walk through a few examples so that you can see my thought process and get a gauge for the timing that it takes to complete most of these problems. I know it seems like a lot of work, but as you get more comfortable with the process and develop some sort of routine for yourself, you'll find that these problems move quicker and quicker. If you've got further questions, please let me know. Send me a message or stop by my classroom. Otherwise, we'll catch up with you again on Monday of next week. Thanks for watching.